So far, we've only explicitly looked at waves and standing waves in one dimension, like on our guitar string. That was a one-dimensional string or oscillator with waves on it. Of course, waves can exist in two dimensions, like waves on the surface of water, and in three dimensions, like sound waves in air. We could similarly derive wave equations in such cases with similar arguments to those we've used for the waves on a string. When we look at waves in two or three dimensions, however, in addition to getting propagating waves and the standing waves that we've looked at, like the waves on a string, we can also get interference between waves that are propagating in different directions. So first, we will look at the wave equation in these higher dimensions, and then we'll look at some basic plane wave solutions of them.
So let's look at the wave equation in three dimensions. We can generalize what we had before. Now we're going to use the gradient squared operator, the del squared operator here, in our three-dimensional wave equation. And we remember that this del squared operator is the sum of these second derivative operators, partial d2 by dx squared plus partial d2 by dy squared plus partial d2 by dz squared. Or equivalently, we can think of this, as I said, as almost like a kind of grad squared. It's del squared operator, the gradient operator dot product times the gradient operator here. And we could write that out in the following way. Note, for the moment, incidentally, I'm going to be using x hat as the unit vector in the x direction, y hat as the unit vector in the y direction, and z hat as the unit vector in the z direction, for a notational reason that will become clear as we go forward. So let's just check on plane wave solutions. If we have monochromatic waves, so some specific frequency, we can get what we call plane wave solutions that are waves that are propagating in a particular direction given by a k vector here, k. So as an exercise in understanding what's going on with wave equations, we're going to check that this wave is in fact a solution of that three-dimensional wave equation. And this is called a plane wave. And as I said before, we're going to be working with these unit vectors, x hat, y hat, and z hat, and that's because we have to use k to represent this actual wave vector here. So we can write r out in terms of its components, x, y, and z, and we can write k out in terms of its components, kx, ky, and kz. So we're going to check that this plane wave is a solution when we choose k equal to omega over c of our wave equation. First, note that we can take the gradient of this entire wave here. We can write out our gradient operator. And what I've done here inside this exponent is I've multiplied out the k dot r. So it is kx times x plus ky times y plus kz times z. So I've written that all out here for us. So let's look at this gradient operation. We'll need to figure out what is d by dx of all of this and what is d by dy of all of this and so on. Well, that's quite straightforward. D by dx of e to the ikx is just ikx times e to the ikx. And that happens for each of the other coordinate directions as well, so we just end up adding up these three parts to get our entire derivative here, our gradient. And of course, that is just k that we have here, and this was just always k dot r, we just multiplied it out. So the gradient of e to the I k dot r minus omega t is ik e to the I k dot r minus omega t. So we can go on to figure out the second derivative here, del squared, of e to the I k dot r minus omega t. And again, remember we can write that as the gradient operator vector dot producted into the gradient operator. So we know the answer to this one. That was just ik e to the I k dot r. And so we can write out this whole vector product here, dot product. This would be I kx d by dx, ky d by dy, kz d by dz. And we know how to take these derivatives because we already did this. And so the net result of that, adding all of these up, is minus kx squared plus ky squared plus kz squared e to the ik dot r minus omega t, which is just minus k squared e to the ik dot r minus omega t. Now, we already worked out the second time derivative of this. That was easy. That was minus omega squared times the same wave. So, with the result we just worked out, for the del squared of e to the ik dot r minus omega t, being minus k squared times e to the ik dot r minus omega t, and choosing k equals omega over c, then if we take this, which we figured out is all of that here, minus 1 over c squared times this, then adding that all up gives us minus k squared plus k squared times e to the ik dot r minus omega t, which of course is just 0. So we verified that this plane wave is indeed a solution of our wave equation for any vector direction k, provided that the magnitude of k is equal to omega over c. So we've checked that these plane wave solutions are indeed solutions of our three-dimensional wave equation. So what does a wave like that look like? Well, here is one particular plane wave with a wave vector k1, and it's propagating in this particular direction shown by the vector down here. Another solution would be a plane wave propagating in this other direction, going along here, with another wave vector k2. And we could add the two of them together. Both of them are solutions of the equation. The equation is linear, so we could get the sum of those two waves. And here we see the interference between those two waves. This is what that net wave, the sum of those two, one propagating in this direction, which was kind of up the way, and one propagating in this direction, which was kind of down the way. And here's the net interference pattern we get from the whole thing. The sum of these two is also solution because of the linearity of the equation. And now we're seeing the phenomenon of interference. These two waves are interfering with one another to give us this different kind of interference pattern.